All right. Welcome to the Space Resources panel, where all your questions will be answered. There were a bunch of questions that were teed up in the last session that I wanted to jump up and say, wait a second, we got a 2-hour panel for this. I'm George Sowers. My background, I think most of you know me, but my background is 30 years in big aerospace with Martin Marietta, Lockheed Martin, and United Launch Alliance. I retired 2.5 years ago as a VP and chief scientist. 2 years ago, I joined the Colorado School of Mines to support the world's first and only graduate program in space resources. So if you're interested in that, I have some flyers outside, but we're in our second full year of the graduate program, and we have 75 students, which is pretty incredible for a graduate program. And I will tell you the program is 100% online, so you can take it from anywhere around the world. We have representatives in our program from 4 different continents, 5 continents now. We just added South America and about 14 countries. And so I'd say about 70% of our students are working professionals like you all that have real jobs. We have NASA employees, we have entrepreneurs, I have an investment banker in Hong Kong. You name it, we've got it in our program, but that just kind of shows you the degree of interest in this field. All right, so our panel today, the theme is how space resources can enable space settlement. I'm the moderator. We have 4 of my esteemed colleagues, folks I've known for years and years. Let's see, Chris Lewicki spent many years at JPL, including operating Mars exploration rovers. His claim to fame, though, was in starting one of the first space resources companies, Planetary Resources, Inc., and now he's moved on to other gigs, and hopefully some of the lessons learned from his experiences can inform the next generation of folks that want to get into the space resource business. Let's see, who's next? Phil Metzger spent 30 years at NASA, where he's one of the founders of the SwampWorks, and we've already talked about SwampWorks here, that is one of the world's foremost labs in space resources. He's now at the University of Central Florida, researching many of the fundamental issues associated with developing space resources. Rob Meyerson, his career trajectory started at NASA and went through Kistler, but his claim to fame is 14 years guiding Blue Origin from a company of 10 people to the powerhouse that it is today with over 1,500 people. That was an incredible accomplishment. About 5 years ago, one of my career highlights was when I was with my former employer, United Launch Alliance, and he was with Blue Origin. We did the deal for the BE-4 engine, where ULA was going to buy that engine, Blue was going to develop it, and fly it on the Vulcan rocket. So that was definitely one of my career highlights. And I remember we had a big rollout in Washington, D.C. at the National Press Club with Tory Bruno and Jeff Bezos side by side, and it's amazing how they kind of look alike a little bit. But announcing this new partnership, and I think it shocked a lot of people around the industry. And then, last but not least, Dennis Wingo was very well known in the community. He's an iconoclast, a professional curmudgeon. But he has a lot of opinions and has thought deeply about this subject for many years, and he's the founder of SkyCorp. So before we turn it over to the panel, I'm going to give a few of my own perspectives on space resources. And when you think about resources, you have to think about economics. And the first point I want to make is that space resources will spur the 3rd great economic revolution for humankind. And so I'll start talking a little bit about human history. All humans evolved, about 100,000 years ago on the plains of Africa, subsisting as hunter-gatherers. One of the proxies for economic wealth is energy capture. And by that measure, hunter-gatherer lifestyle, you can, range in the 4,000 to 5,000 kilocalories per person per day. And the population in those days, which was about 90% of the existence of humans spread across the entire globe and maxed out at around 5 million. So about 10,000 years ago, in what's now the Middle East, some clever hunter-gatherers figured out that if you could save some of the seeds you gathered and replanted them in favorable locations, if you could gather the animals you were hunting together and herd them, you could harvest much more efficiently. You could have a source of milk and meat readily available. That was the agricultural revolution. And in terms of energy capture, it increased from, say, 4,000 or 5,000 kilocalories per person today up to 30,000 kilocalories per person today. And that extra wealth enabled the creation of civilization, writing, cities, civilizations, all those kinds of things. There were downsides, of course. You had disease and war and military and things like that. But the population skyrocketed. And then about 300 years ago, clever Englishmen discovered that these black rocks that they were digging out of the ground could be burned and create steam and drive machines, and that was the start of the Industrial Revolution. That gave rise to the modern industrial economy that we enjoy today. In the industrial West, our average energy capture is up around 230,000 kilocalories per day. And the population has exploded to around 7 billion. Of course, there are unintended consequences of that as well. If you turn on the TV, you'll be bombarded with projections of gloom and doom about how this marvelous lifestyle that we lead today is not sustainable, that we have to change, we have to bomb ourselves back to the farmer or hunter-gatherer lifestyles. But that's where space resources come to play. So compared to the resources on Earth, the resources available in just the inner solar system are nearly infinite. A couple of examples. The power output of the sun is 10 trillion times the power consumption of humanity. Just one small metallic asteroid, say 500 meters in diameter, contains more platinum group metals than have ever been mined. One large metallic asteroid like Psyche in the main belt, which is going to be the subject of a NASA mission in the next few years, contains more metals, enough metals to last the Earth or human race for millions of years at current consumption rate. So the question is, what's the limit? To me, harnessing space resources and bringing them into the economic sphere of humankind will lead essentially to an end of scarcity, an end of poverty, maybe even an end of war. So that's the goal. Harness the resources of the solar system for the benefit of humans. So this table just kind of summarizes what I just said. So how do we start? It starts at the moon. The moon is rich in resources. It has metals, it has rare earth elements, it has helium-3 for potential future use in fusion reactors. But the most important resource that the moon has in the near term is water. Water is essential for life. It makes a really great radiation shielding. But most importantly, in the near term, it can be split into hydrogen and oxygen, which is rocket propellant. In that sense, water is the oil of space. So there's been a lot of recent scientific evidence. If you ask what's changed in the last 10, 15 years, it's our knowledge of the presence of water ice near the lunar poles. The moon is a unique body that has very low obliquity, which is the tilt of the body relative to the sun, which means that if you're near the poles, if you're at a mountaintop, you have nearly permanently sunlit areas. But if you're at a crater bottom, they're permanently shadowed. And those are the areas where we've seen evidence of ice. And this is an image from a recent paper by Shui Li at the University of Hawaii that's showing not only is there evidence of ice, but there's evidence of ice on the surface. And if you're in the mining business and the resource business, then you want the easiest stuff to get. It's an economic proposition. The analogy I use is that, the first gold miners that came to my home state of Colorado picked gold nuggets out of the streams. Nowadays, if you want to get gold from the Colorado mountains, you're blasting tunnels in hard rock and doing a lot of crushing and post-processing to get the gold out. Water ice on the surface at the moon are the gold nuggets of the beginning of the space resource revolution. So I know you were told there would be no math, but I want to hit this point. I'll get a little bit pedantic. I am a professor after all. A little bit pedantic here, and to give you the importance of propellant in space. I spent 30 years in the rocket industry. I fought the rocket equation all my career. It's a tough nut to crack. It's an exponential equation. If you take a look at the form of that equation with the log and you invert it and you solve for propellant mass as a function of delta V, you get curves that go up exponentially. If you hold mass fraction constant, then it actually goes asymptotic vertical. So if you're bringing all your propellant from Earth, there's a fundamental limitation of where you can go, how far you can go. That first vertical equation is with 0 refuelings, and it's delta V as a function of propellant mass. If you can do 1 refueling, you get to that next curve. If you can do 2 refuelings, you can get to that next curve. If you can refuel anytime or anywhere you want, you basically flatten out and completely destroy the tyranny of the rocket equation. It's incredibly, incredibly important. So if you have sources of fuel on the moon, then we can dramatically cut the cost of every activity associated with space exploration or space settlement. And just a couple of quick examples. If we had a source of propellant on the moon to fly from the Earth to the gateway and refuel once along the way, we can cut the cost by a factor of 2. If we're going from Earth to the surface of the moon and we can refuel on the way, we can cut the cost by a factor of 3. If you're going from the surface of the moon to the gateway, you can cut the cost by a factor of 100. So those are the kind of things that we're thinking about. So when we talk about are there markets for space resources, there is a market today for every single mission that goes beyond low Earth orbit will become more or less expensive through the use of space propellant. So every mission, even to GSO, every mission to GSO can become cheaper using refueling with lunar source propellant. So at the Colorado School of Mines, we're working on a lot of different ways to extract this water. This is an artist concept of one particular architecture. This is kind of the minimum viable, economically sustainable lunar mining operation. The basic idea is that we're reflecting sunlight from crater rims into the crater bottoms, using that sunlight directed to the surface to sublimate ice that's on or near the surface. It's captured under that dome-like structure that you see there, routed into cold traps that are attached, and then those cold traps are trundled off. I've got a NIAC grant right now that we're actually creating icy regolith simulants and testing them in our cryogenic vacuum chamber at the School of Mines to look at how much sublimation we can get just by direct heating with illumination. And I'll close with a quote from John Marburger. He was President Bush the Jr.'s science advisor back in 2006, one of the other times we were going to the moon. But he recognized the economic importance of the moon, and that was its importance. It's not about science, it's about money. If we can make money in space, space settlement will happen. Absolutely. Just like when there was gold found in California and Colorado, the towns followed the money. So with that, I'm going to turn it over to my esteemed colleagues here, and who wants to go first? Just go in order. Chris?
Go for it, Chris. Okay. Good afternoon, everyone. Thank you for caring enough about space colonization to be here today. So I'll start off our session this afternoon with some reflections and just kind of a reminder, it's a really good time to be doing things in space. It's not as good as it's going to be in 20 years. It's not as bad as it was 20 years ago. But right now, you know, I think this is a present. There's a lot of great things going on that are a result of a lot of hard work by a lot of different people. And I started out in the public sector, now in the private sector, have worked about equal periods in both worlds. I think the exciting thing about what we are transitioning into is there being much more private and essentially just non-government activity and funds going into various things related to space. They might be going largely into serving markets here on Earth, creating internet around the world from 4 different providers, but all of that has a lot of good developments that create a lot of opportunity and great momentum. Speaking to the choir a little bit in this room, but one thing that I like to remind people about space colonization, space development, moving out into space is that there's not some bright, new, different, never seen before future there. It's just us continuing to do things we've always done. Doing them in a new location, doing them with newer technology, trying to create more opportunity than the folks before us had. And we're all interested in that because space has the unlimited potential for us to do that. But I think it's taking a step back at it and looking at, you know, we're creating new cities, we're creating new destinations, we're creating new transportation networks, we're creating new ways of doing financing and selling things to each other and creating value so that people want to continue doing that. It's actually not going to be any different. And the fundamentals of it are pretty much going to be the same. There are going to be people who do it because it's there. There are going to be people who are doing it because it's a fun hobby or it's a very interesting pastime. And there are going to be people who do it because their life depends on it. Or because they're fleeing something. And all those have been present throughout most human history, and I think as long as we continue to be emotional humans, they will continue to be present in the future. One thing at looking at 20 years of private development of access to space, I think a lot of people look at those curves and think about, you know, we'll get to thousands of launches per year, and getting into space will be so cheap there won't be any reason to do anything in space because we can just send it for free from the ground. And FedEx and UPS and DHL haven't figured out that business model yet in terms of we shipping everything everywhere. So in a lot of ways, I think we need to appreciate that the cheaper that things get, the more economic activity there will be, the more opportunity there will be for doing things on site. So in this way, the reductions of launch costs do a lot to help accelerate things. And we are, we're well in the middle of that with a lot of exciting things still to come. But this change that has been obvious by engineering standpoints, but nearly impossible by every other measure, is starting to change as the result of the good work going at SpaceX and Blue Origin, Virgin, and all the other folks that have been working the tyranny of the rocket equation. And I'll just, thank you for the ride while you're doing that. To jump into the resource and mining aspect of things, the last few years at Planetary Resources, we got much more involved in the economic geology of things and understanding, in the world of space resource exploration, how does this map to terrestrial resource exploration and development? And there's this curve that's shown, whether it's in a geologist's document or in the tax code or in an investment prospectus, it's this general curve, and that it takes a long time to do these projects. There are things along the way where money changes hands, value gets created, and many times the project itself changes hands. And there might be 4 different businesses from the beginning of this curve where you're trying to find opportunities and resources to the end of the curve, where you're actually delivering raw materials from a resource. We had found really an economically viable way at Planetary Resources to fit the space model in that. But the challenging part, of course, is how to get from that first part. I would say we're still in the pre-discovery phase in space. We're doing a lot with planetary science. There's 2 active spacecraft out there right now, Hayabusa 2 and OSIRIS-REx, that are acquiring samples. Not quite en route back to Earth with them yet, but those aren't commercially focused mining prospect missions. Their purpose was a scientific one, and I certainly wouldn't bet the future of a mine based on going one place once, acquiring one sample, with the particular focus that those missions have. They'll be very helpful, but prospecting in space requires a more diversified approach than that. So this is really what we have in front of us with any destination, with any resource that we're looking to garner from space. And we're farther along in this now than we were 10, 20, or 30 years ago, and we still have a very, very long way to go. So to start the conversation in our panel this afternoon, a few very high-level things, my takeaways from 10 years at Planetary Resources, and this is a much abridged version. There's probably still a book that I could describe of it. The unstated thing that's not on this chart of yes, well, of course it was too early. By definition, it was too early. Whether you're 2 guys in a garage making a new computer in the 70s, people were all there to tell you no one wants personal computers yet. It was by sheer will of those people and good fortune and timing that they created an industry. And that was our intent in Planetary Resources, was to see if we could get enough of the magic together to create that industry. And I would say, time will tell. We're not there yet. The statement on the chart is a very long-learned and detailed lesson, which I could say a lot about. But the summary is, we haven't figured out how to privately or publicly finance long-term, high-risk, capital-intensive projects. The government models don't exist for it unless we're at war. The private models from financing don't exist for it either. There's a few notable exceptions, which involve well-heeled individuals who are very passionate about a particular subject, but they're focused on their subjects, and if you want them to focus on your subject, you need to find a new one. Not a new subject, you need to find a new passionate individual who is well-heeled. So I could say a lot more about that, but really it all comes back to that the financing models today don't support things like that. It doesn't work in the venture capitalist model, it doesn't work in the crowdfunding model, it doesn't work in the nonprofit model, at least not to the scale that it needs to. And this is at the level of hundreds of millions to billions of dollars, which is freely available for a variety of topics, just not this one yet. There's been a lot of progress from an engineering standpoint. There's been a lot of progress from a science standpoint where we know way more about this subject than we even knew 5, 10, or 15 years ago. And the US, Europeans, Chinese, and the Japanese have all been contributing an immense amount to our knowledge of space as a place and space as resources. And that has been enabling lots of things. What we've seen in the access to space with people investing their money in that area is really demonstrating the art of the possible. A lot of us in this room know that these things are, there's no equation that prevents any of these things from happening. It's just focus and willpower. And we've got a number of examples of the inevitable things that focus and willpower can enable in the launch vehicle market and the technologies that we're enabling. I think we discovered at Planetary Resources in 10 years that there does exist a viable mining industry grade resource prospecting plan, where resource prospecting is a tens of millions to hundreds of millions dollar affair, whether you're looking for a gold mine, a moon mine, or an asteroid mine. And that's something that there is enough data, both scientifically, technically, and economically to justify that investment and to stand the same level of scrutiny that any terrestrial plan does. One of our theories of planetary resources was the aligned revenue, in that we take subjects that are technically related to things that we would need to do anyway, and we try to create revenue opportunities, even try to create scalable businesses for them. And that is a trick that I don't think anyone has figured out yet. The idea of starting a company that you do this one thing today so that 10 or 15 years from now, you might be able to pivot it in to that big thing. I haven't seen an example, and we weren't able to create an example which is able to bootstrap from SBIRs and private contracts into $1 billion of funding. So that's an unsolved problem. It may still be possible. There might be some bright spots that I'm not bringing emphasis to, but for space resources, I wouldn't recommend anyone pursuing that model today if space mining is your outcome. If your outcome is technologies that support space mining and you don't plan on doing it, that's still, I think, a good opportunity to pursue. Second to last here, governments, at least for planetary resources, and I'm speaking about more than one, and not just the ones that are in the news, but we had a lot of access to high levels of governments all around the world, a lot of wonderful conversations, and I would say I wouldn't bet anything on any of them. That should be like your plan E or your plan F. And plan A, you need to be doing things for your own reasons and for your benefactor and for your team's reasons. And if an engagement with any government helps you meet that end, by all means, but certainly don't plan your business around it. And then the last thing, which is something that we can explore a little bit more throughout the course of the panel, is that I have come to recognize with the many conversations that we've had with billionaire investors, with venture capital funds, with strategic investors, with family offices, with governments, that the current financial world that exists, we don't remember that venture capitalists were a thing that was invented, and it's a few decades old. And even our concept of the bond market and the stock market aren't more than a century old. And we created these things to solve particular types of problems to the things that we wanted to do. We don't often think of it as a creative discipline or an engineering discipline, but financial engineering is definitely a thing. And it enables the world that we live in today. And the environment that exists in the mining community, the community that it would be most aligned to perpetuating and extending their value proposition in their business, that model is currently, in my opinion, not translatable into space for lack of a particular type of a regulatory environment, which mostly relates to the financial environment that regulatory environment has. If you, one of the things that mining companies can do is make an investment of 10, 100, or $100 million or $1 billion. And their backstop on that being a bad investment is that they can write it down. And they can actually balance their portfolio in tax obligations against things that are going extremely well, that they maybe worked 10, 15, 20 years on investing in, that are now making so much money that they don't want to lose it all in taxes, that they're willing to take some very high risks and speculative bets in those projects that are going to be their cash cow 20, 30 years from now. And the regulatory environment that exists in the mining and the energy and oil and gas world in many pockets of the world allows them to deploy that amount of capital at that high level of risk for that duration of time that makes it okay. It's a known thing. It's kind of, it's like a big pharma startup. It takes billions of dollars, but eventually when you get your drug approved, you make billions more. So that does not yet exist in space. We tried very hard to move it forward with a lot of activity at Planetary Resources, and we did move it forward, but it's not moved far enough. And I think much more than any technology problem, much more than any particular access to funds problem from an investment standpoint or a business plan, this particular aspect of financial engineering is probably something where we need to see a new invention or a new event that will cause new things to happen. So I'll leave you in mystery with those comments right now and let the next person take the stage. My favorite tagline, the most important resource in space is people. The man created.
All right, who wants to go next? Rob? Or don't, Dennis? Okay, we'll just go down the line.
Thanks, everybody, for being here today. And a little over 30 years from when I first started in this arena, my background was actually in the computer industry, and where we changed the world. Microcomputers. I helped build the world's first 1 gigabyte hard drives, the first terabyte servers, and a lot of fun stuff. But I wanted to do space. And in 1988, I went to a school in Huntsville, Alabama, called the University of Alabama, Huntsville, because they were doing space, and I wanted to do space. I got very lucky, met some of the original German rocket scientists and learned some of the trade in space from them. I wanted to do engineering and physics, and the university had a program that would allow me to do both. But much more than that, we were flying hardware, and I built computers. I helped build tens of thousands of computers, hundreds of servers, dozens of artificial intelligence machines, and I like building things. And building things in space, that's what I wanted to do. And in 1989, this organization, the Space Studies Institute, had a really cool project called Lunar Prospector. And Lunar Prospector had a name chosen. Henry, were you there in the beginning with Lunar Prospector? That name was picked for a reason. We wanted to go beyond the science, because up until that time, the moon, Mars, space in general, and robotic and human exploration was about science. And we wanted to go beyond that, and so we picked a name, Lunar Prospector. And we even had this cool sticker that Jim Davidson, I believe, from the Houston Space Society made of the guy with a mule, and the mule's got his astronaut suit on, and the guy walking with the mule has that. And so we wanted to create a different vision and a different mindset. Well, Lunar Prospector, in April of 1989, we wrote the RFP at Space Studies Institute. Gerry was still with us at that time. And we had a lot of incredible people there. I got to know a lot of folks, many of whom I know today, and unfortunately, many of them who were in the prime of their life then, who thought we would be going back to the moon in a few years, are no longer with us. And their dream died in their lifetime. And so, but we wanted to push that, and we wanted to push the project. It was the world's first private lunar orbiting vehicle. Now, you think Chris, and I know Chris had, we're all pushing this rope, but back then, private lunar exploration, that was unheard of. But Gerry and the Space Studies Institute pushed that. And it allowed us to get a bunch of people. We had a meeting in Houston, Texas, the first meeting. There were 300 people from NASA JSC came to this first meeting. And we came up with a set of instruments, had the design, had this company do some of the work, and the project moved on and eventually flew as NASA's first return to the moon in 1998. And it was the one, along with Clementine, which flew earlier in 1994, also by someone who was very supportive of the Space Studies Institute, this maverick colonel by the name of Pete Worden, who many of you know and who now works for Yuri Milner and the Starship project, a lot of the stuff that he's doing to send stuff out of the solar system. Between Clementine and Lunar Prospector, the first indications of lunar water were given. But on top of that, we had something really cool, and this, in my opinion, is the value of the Apollo program. We brought back 843 pounds of rocks, and I can tell you that every single bit of remote sensing that we do around the moon today is dependent on those 843 pounds of lunar rocks for the ground truth. Along with a couple of Soviet sample missions that they have, and hopefully China will be doing a sample return. And there's been a few meteorites, and people like Steve Jurvetson, the billionaire venture capitalist in Silicon Valley, he has his own lunar meteorite. But we started that back then, and in 1989, as a student, I didn't have any of these gray hairs. It was even before I don't think Chris was out of high school yet at that time. NASA had this big, we're going back to the moon, the Space Exploration Initiative, and all these big NASA officials were up there, and this is all what we're going to do. And the very first time I ever stood up in front of a microphone, and I said, look, you people have been talking about this for 20 years. When are you going to do it? And that kind of kicked off my curmudgeon-y at a young age in this area. And we do this, and so Lunar Prospector went on, and it was able to fly, and then we had another return to the moon called the Vision for Space Exploration, of which I was involved with, and I know George was involved with. I know some of the people in this room were involved with, and we were moving forward. We were doing all this work, and then the political winds changed again, and then, we've been there and done that to the moon. We're going to go to Mars. Well, Werner von Braun said one time, there's no big deal going to the moon or going to Mars. It just takes more money. If we can't get the money to go to the moon, why do people think we're going to get the money to go to Mars? And so that has always been one of my existential, let's call it conflicts in the whole thing. And my buddy Bob Zubrin and I, we both are in agreement. We want to go to Mars. We want to settle Mars. We want to take Mars. We want to industrialize Mars. But we have to do things in a manner that is consistent, that we can actually do. Chris talks about the gap, let's call it the gap between where they're at and where we want to be. At the end of the day, that gap is all about, do people believe your story? It's like Paul Spudis. For decades, the results of Lunar Prospector, and it all started, the lunar water started with a professor by the name of Dr. Jim Arnold. He was at NASA, but he was at the University of California, San Diego. He wrote a paper doing a thermal analysis that said that water ice looks like it could exist in the polar regions of the moon. Well, when Lunar Prospector went and when Clementine went, great data. It looks like there's water there. Paul Spudis, who just left us this past year, almost a year ago this week, Dr. Paul Spudis passed away. And Paul was the leading proponent of this, and he did the papers, and he showed, and Stu Nazet, who's now in prison, and other folks who were doing the space science, and it all started working, but people didn't believe it. It was only in 2009, when there was a confluence of Lunar Reconnaissance Orbiter, the reanalysis of Galileo data from a 1990 flyby of the moon, and the Chandrayaan orbiter, the Japanese orbiter, that we finally created and brought the confidence level up about lunar water to where it wasn't, okay, we believe it. It's like, okay, we can't deny it anymore. Because I can tell you, I was a PI on a NASA mission that's called Lunar Resource Mapper in 1993, and the money was taken back by Congress after the contract was awarded to Boeing, and I worked right up here in Renton with the Boeing folks. I was one of the PIs on that mission. And they said, if that spacecraft goes and if they find water, that's going to allow George Bush to be able to take us to the moon, and we can't have that. And so this is some of the things. They talk about political reality. Chris talks about that. And that's one of the political realities that we go with as well. So this is about resources and space settlement, but it's about getting there. It's about believability. And so we have very laboriously and with great effort have brought the level of believability enough up to where George now has 75 students doing resources. We have a young generation now that a lot of people want to do this. A lot of the young people are really, really into it, and it's really cool to see on Twitter. And I first met Chris in about 92 or 93 when he was a young freshman at the University of Arizona, and I was building a student satellite called SEDSAT. And Chris says, I want to build your ground station. It's like, oh, right. And this is the kind of people that you want. You want people with enthusiasm, but you want to give those people with enthusiasm something to do that's cool. So we've continued on, and the vision for space exploration, and now we're doing it again. Well, and I don't remember your name, but you're saying, when are we going to have the first ISRU? Well, we're going to have it when we get there. But we actually have had ISRU developments. Dr. Larry Taylor at the University of Tennessee showed that sticking lunar regolith in a microwave oven, he could heat it to 2,000 degrees centigrade in 30 seconds. That was a huge breakthrough. Most people don't realize it yet. But it's a way to heat the regolith up to be able to use it, to be able to do sintering, to be able to do a lot of cool stuff. And so this is what I work on. I'm working on the very difficult stuff. Like right now, I just had a meeting a couple of weeks ago with a high NASA official, and I said, look, NASA right now doesn't have a lunar surface strategy. People are playing with a lot of bright, shiny objects. We have a gateway, we have Artemis lander, we have this, but nobody is working the lunar surface systems. What are we going to do on the surface? And so what I have been a proponent of is a lunar industrial site on the moon. Again, we pick words carefully. We pick the word industrial. And we want to do material science here. You talk about what are we going to do? Well, if you take a look, our good friend Elon Musk said, look, if there was crack cocaine on the moon, it wouldn't make sense for me to ship it back. I couldn't make money on it. And he's actually right when he makes that statement. But it's also a challenge. What can we bring back? And there's no silver bullet. But there's a bunch of bronze ones. There's a lot of different things we can do. George talks about water, and he's exactly right. Water is absolutely necessary for transportation. Water is absolutely necessary for so many things that we want to do, but it's not sufficient. It's not sufficient if you want to do industrialization. If we want to go and mine regolith and go after helium-3, great, or no matter the economics of that for a second, or these other things that we want to, and I wrote my book on platinum group metals and bringing them back to the earth and ran the economics on that, and it's interesting, but it doesn't quite get you there. But if you have a lot of different activities, so if you have a lot of different activities, and I want to go into a couple of more, and I got Elon on this one. Right now, we're building a nuclear fusion test reactor called ITER. I believe it's in Spain. And in order for that to work, you have to have these portholes that these very powerful electrical connections and all go through, and they're using diamond glass. This diamond glass is $3 million for a 6-inch in diameter piece of diamond glass. But if you think of diamond glass, what if that diamond glass was $100,000 an ounce or $250,000 an ounce? On the moon, there's definitely carbon, we know that, and how they make the diamond glass is through vapor phase chemical deposition in ultra-high vacuum. So just think, can we do that? It's possible. I've done the work, and you can talk to me in the session. But there's one. Sapphire. 35% of the moon is aluminum oxide. Well, aluminum oxide with a chromium admixture is sapphire. Guess what almost every single substrate of advanced silicon is today? It's sapphire, silicon on insulator. And other technologies, there's one of our big problems right now in the semiconductor industry is getting rid of heat. We've got 10 billion transistors on one chip in your iPhone. They're coming up against the thermal limits. Well, there's a form of silicon, it's called silicon-28. The silicon that's in our chips is a mixture of silicon-28, silicon-30, and silicon-31. Well, that's called isotropic silicon. If you could separate it out, and you can, we did this a long time ago, it's called vacuum diffusion, which is how we created the uranium for the uranium bomb, but you can also do this for silicon. And there was a company in Russia that was doing that. It was too expensive. But if you're on the moon, and if you have an infrastructure that's already doing things similarly in a different area, then it might make sense to do silicon-28 substrates or boules. And if you can ship that boule back for a reasonable price, you buy a flight back from Rob here at Blue Origin and bring it back at a reasonable price. There starts to be different things you can do. And so this is what I work on, and what I've been talking with NASA about is the infrastructure that it requires to be able to do these types of things. If you read, we had an event, and I'm going to terminate here real quick, in 2014 at Draper Fisher Jurvetson, and there was a bunch of people get together, and Steve Jurvetson said, look, I've got 5 friends that they could write $1 billion check and not miss a zero, but they need a compelling argument. So the paper that I came out with is, where do you have a site? I like the North Pole, NASA likes the South Pole. It's not really worth quibbling about. But if you're in the polar regions, you don't have to have nuclear power, so you just cut your cost a whole lot. And if you land these landers, and we designed one, it's called a power lander with 100 kilowatts per lander, and it will fit on a Blue Moon lander, 100 kilowatt lander. So these guys are already building a critical piece of transportation infrastructure. And Amazon, at the end of the day, just like Walmart, is a logistics company. Walmart took over retailing in the 1990s because they understood logistics. Amazon did the same thing recently. So it's logistics, it's infrastructure, and then it's product. These things all coming together is how we're going to make the moon work, and that's what I'm working on. And thank you very much.
Okay, I'm Phil Metzger, and thanks for having me here today. I worked with NASA for about 30 years, co-founded the Swamp Works, where we were developing technologies for mining and manufacturing in space. And while I was there working on these technologies, I got the bug for space settlement because I realized the technologies that we were developing for NASA to support sortie missions to do science could have a broader application to revolutionize the nature of human civilization. So I got excited about that and have continued working in this field. So I'm going to shift gears a little bit. I want to talk a little more philosophically about the nature of space resources, because I hear people criticizing space resources. They always use the same arguments. They'll say, well, if you think you can do things economically on the moon, why aren't people doing it in Antarctica? Because Antarctica is a lot closer. It's resource poor on the surface, and I don't see a lot of people who want to go live in Antarctica. Or they'll say space transportation is becoming so cheap that we could just launch everything from the Earth, and trying to put industry in space will never be able to keep up with the plummeting cost of transportation in space. Well, historically, that argument makes no sense at all, because historically, whenever you create cheap transportation to a new region, it doesn't have the effect of isolating that region economically from the rest of human civilization. It's the opposite. You integrate that region into human civilization. And so people there start creating industry and learning how to develop the resources. But I want to address philosophically, how can we take the ordinary, uneconomic resources of space and turn it into something extraordinary for human civilization? So the moon, it looks like this. Mars looks like this. Okay, let's see if we can see anything common in these places. Titan looks like this. Asteroids look like this. So they all have several resources in common. They have sunlight, they have regolith, and they typically have some kind of volatiles, either the atmosphere or locked in the regolith. There's typically some kind of volatiles available. But Earth looks like this. And Earth is really a lot different. This is our home, and the reason this is our home is because it has a biosphere which has been transforming the resources of our planet over billions of years, taking the minerals, breaking them down, creating topsoil, and then more complex life forms come in and colonize the continents, and then even more complex life, and then finally human civilization. And for 10,000 years, we've been developing, since the agricultural revolution, over the last 10,000 years, we've been developing this complex industrial supply chain where we're manufacturing and we're transporting, and we've been exploring the world and finding all the special deposits of resources. We've learned how to exploit this body, this complex world that we live in. So how do we take this experience and learn how to do that in these other bodies where there is no biosphere? There hasn't been billions of years of reprocessing of the materials through biology and 10,000 years of industrial development. So here on the Earth, the terrestrial supply chain looks like this. We've got the natural resources, then the single-celled life, the multicellular life, all the way up to humans, and then humans have developed machines. And I put it in the sequence of dependence. So every level depends on the existence of the next lower level. And the machines require us to be here for them to exist. But space today looks like this. You've got the natural resources on these geologically simpler bodies, and then you've got the machines, and then you've got the humans that depend on the machines. We couldn't go to space without the machines. And we're missing all those intermediate levels. So philosophically, that's the problem. And then I mentioned that they are geologically simpler bodies. They don't, some of them, like the asteroids, they haven't had the reprocessing from underground hydrology, concentrating ore bodies like the Earth has had. On the Earth, you'll dig these shafts to get to the ore body, and all that rock that you cut out, the country rock, you throw into a slag pile because it's not economically valuable. When they say it's not economically valuable, that means the energy, the effort that you put into processing the material wouldn't pay back a net profit. You would end up being worse off for the effort, so we don't do it. But on Earth, at the surface of these bodies, without having lots and lots of exploration, everything is country rock. Everything is the stuff that you would just throw away on the Earth. So if we throw it away on the Earth, how do we think we're going to economically make benefit out of it and have a better existence for humanity when you have on top of that the harsh environment and all the transportation issues? Okay, so this is what I want to explain. Space right now is hard because the humans have to take care of the machines, which we depend on to exist. It takes up a lot of our time. Astronauts spend a lot of their time taking care of the machines. And it's also very expensive. Because of that lack of a supply chain, we have to bring a lot of stuff from Earth, which makes it expensive. So Earth is easy because all of that stuff underneath us, we don't necessarily have to take care of it. Long before humans started learning how to take care of the environment, it existed, and we were able to live here. We don't have to go out and tell each plankton in the ocean what to do. It just does it. It's all autonomous in general. So what we need is a better in-space supply chain. We need to have those missing layers, which are going to process the resources, and we need them to be largely autonomous so that we're not sitting there taking care of all the machines that are doing all the processing for us. Okay, so that's fundamentally what we have to do to make space economic so that human life will be better by going there. In a very simple view, I forgot this was a lot of clicks. I'm just going to click through all these. In a simplistic early stage, the mining and manufacturing might look like this. We'll mine the rock and the regolith. We'll extract the different elements. We'll also mine the polar ices. We'll get the nitrogen and carbon as well as the water, do some materials processing, and then we can do construction and manufacturing, make robots, make the fabrication hardware, make solar cells, which provide the power to do all of this. I've run numbers on this. The whole system does have a positive metabolism. You can make easily 30 times more solar cells than you need per generation to replicate itself. You can create 30 times more energy than you need and still have a replication cycle of like every 2 years. So there's a positive metabolism in this. So there's no economic issue with metabolically. And then once we've got the system, it can produce benefits, and we can have early stage benefits like making rocket fuel, which George talked about, which might help setting it up. A more advanced view, it might look something like this, breaking down the elements and doing a lot more steps in the manufacturing. And that's very possible because the lunar regolith, even though it's country rock, it's got silicon, oxygen, iron, calcium, aluminum, magnesium, other things like rare earth elements are available. The lunar ice, oops, what am I doing wrong here? The lunar ice, we know, has chemistry something like this. This is derived by the L-cross impact. It's got ammonia, it has carbon compounds, and as well as a lot of water. And so the moon isn't lacking anything we need to set up a full industrial supply chain. The elements are there. A few years ago, we did a Keck study on how to do construction in space, and I wrote some tables that went into the paper where we laid out different levels of lunar industry processing to make different materials. And the second column there shows which rows build upon which other rows. And so you could do a series of developmental steps to build up more complex processing of the materials. We've looked at this for asteroids. We've looked at it for Mars. In the end result, I've borrowed a picture from the 1980 Ames summer study, which looked at a self-replicating factory. This factory was aiming for 80% closure, meaning 80% of its materials could be made by the factory, and you have to bring 20% from the Earth. And they estimated that this factory would only need to have about 100 tons of equipment. We've looked at this, like what would it take to get closer to 100% closure with more modern technology, and it's probably just in the hundreds of tons to get a full closed supply chain that's much closer to 100% closure. So this would be the goal. The question is, what are these economically viable intermediate steps to develop these pieces of industry? And that's what we've been talking about a lot so far today. NASA has been developing some of the technologies. This was a field test I was at on Mauna Kea, where we were mining the regolith, processing it, and making rocket fuel out of the dust, out of the volcanic ash. And we were firing a rocket, so we called it dust to thrust. So NASA has been investing, developing pieces of the technologies. But NASA's really only looking at what technologies will support its exploration. Commercial companies have been looking at how can we go beyond that? How can we set up the full supply chain? What can we do that's economically viable? I think there are basically, in broad terms, three ways to pay for this. One is commercial, find business models that make sense. It is challenging in the early stages, trying to find the stepping stones. The second effort would be having the government pay for it as a public effort, where you tax the people, you have visionary leaders who say, let's do this because it's good in the long run. So you just simply tax and pay for it. And it really isn't going to be that expensive to do it. It would take a minority fraction of NASA's budget for several decades, and then you're done. Very, very doable. A third approach would be private philanthropy. So the billionaires who are investing, or the Open Lunar Foundation, which just recently announced its existence. Any of those three methods will contribute, I think. I think they're all going to contribute. But in order to find business models, you need to find things that are economic in the short run. And philosophically, I was trying to explain, why does doing this in space make sense in the long run? Why can we take that country rock that we would throw away here on the Earth? How does mining that make humanity better overall? Well, economic is a human-centric metric. It's not the metabolism, it's not the energy that matters, it doesn't make our life better. And right now, here on the Earth, we're doing things that were uneconomic a few hundred years ago. Like, nobody would have ever spent their time to create plastic bottles filled with water a few decades ago. It was uneconomic. There was no profit in doing that. Go back 1,000 years ago, people would have never, several thousand years ago, people, well, let's say 50,000 years ago, nobody would have ever spent the time to make a podium like this because there was no economic value in it. But as human civilization has progressed, we've continually made activities that were uneconomic to become economic. And the way we've done it is by leveraging our labor in the industrial supply chain. Right now, if you add up all the machines in our culture that are doing economically valuable work, they're spending 8.5 times 10 to the 16 joules every year doing mining and manufacturing. If you add up, I'm sorry, that's the humans. The machines are doing 10 to the 20 joules per year of work. If you took a human being and asked what is the most thermodynamic work they could do 8 hours a day all year long and added up for all the humans, it would add up to, in the US, 8.5 times 10 to the 16. So right now here in the United States, machines are doing 1,200 times more work than humans could possibly do if we were all working as hard as we could possibly work. So we've leveraged ourselves more than 1,000 to 1. And all of this stuff that you see in the room, they were made 99.9% by machines, 0.1% by the contribution of humans, other than our minds. The physical labor was 0.1% human, 99.9% machines. And it's this leveraging, which we have continually improved throughout the course of civilization, that has made new activities become economic that previously weren't. So the question is, how do we increase civilization? How do we do greater things than we've done before? The answer is more leveraging of our labor. If we want to do greater things, we need more leveraging. The one resource that space has that Earth can never have is more space. We are living on a finite planet, and we just can't fit an infinite number of machines on the planet. When you put more machines in space, that additional leveraging causes the mining of country rock to become economically valuable because it has positive metabolism. And then we can do greater things that are beyond the limit of what a single planet can support. So philosophically, that's how we do it. But the one last thing I want to mention as a key is that we can't leverage ourselves more if we have to control all the machines. And so the key to making this all work is artificial intelligence, machine learning, having smarter machines so that we have more machines per person managing them. Okay? That's the answer, I think.
Thank you, George. Thanks, everyone. I'm the recovering launch vehicle guy here today, so not a resources person yet, but I'll play one today. And first off, we can all agree that there's a lot of work to do before we can achieve this grand vision of O'Neill. And it'll take decades of investment and programs bigger than a combination of Apollo and the Manhattan Project and the Interstate Highway System, the Transcontinental Railroad, GPS, combined. So, and I'll throw in the Deep Space Network too. So, and I did that for a reason because infrastructure is something that we need to focus on to proceed settlement. And so using these resources is a way to get that can help us get to that infrastructure as well. I'm talking about something that's going to cost hundreds of billions of dollars and maybe even trillions of dollars. And yes, I'm talking about something that's going to cost more than any one person can afford to invest in one company. Public-private partnerships, I'm a big fan of. They're a great model, but a PPP won't get out of the gate without a market for that outcome. So we have to think about where those markets are going to be. So first off, you want to start, with why are people going to want to live in space? And I think about looking at the 1800s and why did people want to go west? They went west for the gold rush. They also went west to get a place of their own. And then they also went west to get away from something that they didn't want to be burdened by, like growth or government or something else. And so I'll get to a point here. It's been 50 years since Apollo, but we're still very much in the infancy of our space program. And I look at it as we're here at the Museum of Flight. We really haven't invented our DC-3 for space yet. And there's still so much to do. And I think that we're going to need to embrace real innovation and take some risks while we figure out what that DC-3 is. Not just for getting from, from Earth to orbit, and you might argue we've already got it, the DC-3 there, but for getting from Earth orbit to the moon, getting to the lunar surface, getting back. And so all of those things need to be put in place along with that infrastructure to support settlement. And so that's why I'm a big fan of CLPS. And I want to talk a little bit about CLPS. And CLPS is NASA's Commercial Lunar Payload Services contract or program. It's a 10-year, $2.6 billion IDIQ, indefinite delivery, indefinite quantity contract to spur lunar surface exploration. And it's the brainchild of Dr. Thomas Zurbuchen, the head of NASA's Science Mission Directorate, and it holds great promise for spurring future commercial development of the moon. And the RFP was released about a year ago. NASA announced the first CLPS cohort in November of last year, and the requirements for this are really, really simple. It's deliver a minimum of 10 kilograms to the surface by 2021. And providers acquire the launch, and they integrate the payloads, and it's just very, very simple. So what NASA said is they're expecting to fly 2 CLPS missions per year to provide a steady base of, quote, government business for companies developing lunar landers with the goal of fostering commercial business models for deep space exploration. Personally, I'd like to see them double that and do 4 missions a year or more, but I think over time we're going to find the benefit there, and it starts with prospecting, some of the things that my peers on the panel are talking about. So with the number of commercial landers in development and pricing announced and pricing known, a series of these prospecting missions could be planned and to accurately inventory the resources on the moon by location. And better understanding those resources is going to allow us to provide the data we need to go build a business model that we need to go figure out what it's going to take to go close. And that could support these future space settlements. So what I'm trying to do is come back to what we need to do today, and I think CLPS is a really good model there. So the initial cohort of CLPS companies that are out there right now, there's 9 of them. The first of them is Astrobotic Technology out of Pittsburgh. They're affiliated with Carnegie Mellon. Deep Space Systems is a small company out of Littleton, Colorado. Draper Labs, you probably heard of them, out of Cambridge, Mass., first contractor on the Apollo program. Firefly Aerospace out of Cedar Park, Texas, right outside of Austin, more known for launch than lunar landers, but they've got a lot going on there. Intuitive Machines out of Houston. Lockheed Martin Space, might have heard of them. So Maston Space Systems out of Mojave, Moon Express out of Cape Canaveral, and Orbit Beyond out of Edison, New Jersey. And so this is a combination of very large and some very small companies, some familiar names, some were part of the Google Lunar X Prize very recently. There's some surprising exclusions out of this, and as I've watched this, I've seen some very creative partnerships get formed as part of the CLPS cohort. For example, Orbit Beyond teamed up with Team Indus, which is one of the former Google Lunar X Prize team. Draper's teamed up with iSpace from Japan, and then Firefly has teamed up with IAI, the creator of the Bearsheet lander, and so they're looking to, in all these cases, they're looking to license that design and build it here in the U.S. On May 31st, NASA announced the first 3 contract awards to deliver payloads to the lunar surface, each one going to a different site on the moon. And I think this is lightning fast for NASA. And I believe the speed at which NASA is moving on CLPS has really caught a lot of people by surprise, and I think in a really good way. So it's something that we should be paying attention to. One of the awards went to Astrobotic, which plans to land the Peregrine lander in July 2021. The company will launch on an Atlas V, and they received $79.5 million for carrying up to 14 payloads on the Peregrine lander. Intuitive Machines plans to launch its Nova-C lander on a Falcon 9 in July 2021. And this is a $77 million contract to carry up to 4 payloads. And then Orbit Beyond was planning to launch its Z01 lander on a SpaceX Falcon 9 in September 2020. They were awarded $97 million from NASA to fly up to 4 payloads. And shortly after an announcement, they withdrew from the first task order, but they're still eligible for future CLPS work. And I don't know the details of why they dropped out, but I don't think it was money. And so when you look at contracts, those 3 contracts are in the $79 to $97 million range. I think Bearsheet is an existence proof for a $100 million lander. I've talked to friends in the industry, some that work rideshare, and $80 to $100 million is doable for these kinds of companies. So I think there's a lot of promise as we look forward. CLIPS is moving fast, and it's going to provide us the platform for prospecting and technology development that's going to help get humans to the moon very soon. So thank you, Dr. Thomas E. Buchan, for all your great work there. And NASA is now soliciting inputs for the next team or teams to work on the next phase of CLIPS, which is a larger lander. I've heard up to 350 kilograms. So we'll see who gets selected for that next round and how the next set of task orders that come out. NASA's also moving fast in some other areas. There's a program called Lunar Surface and Instrumentation and Technology. They awarded to Astrobotic a rover called Moon Ranger recently, and so Astrobotic's going to build this rover to fly on their CLIPS lander, and I'd like to see that CLIPS mechanism and these similar mechanisms be used to do other creative things on the CLIPS landers in the future. So there's a lot that can be done. I'll close with the Dear NASA letter, so I'm not going to read it all the way through, but the behavior that we need from NASA to spark development of a robust commercial market for Moon and Mars exploration. First off, it's incentivize outcomes, and I think customers readily demand that their payloads get delivered softly, and precisely. So NASA doesn't always need to prescribe requirements to make that so, because customers demand that. And experimentation like the kind that's going to be done on CLIPS is really going to lead to new innovations, and we just need to spur that. We need to encourage that. Second thing is be predictable. I think private investors are very excited about space, but they're leery about NASA because the agency is seen as fickle and changing its mind with each new administration, and we really just need that predictability so that investors can come in and know that their investment is going to turn into a real product. So being consistent is a key thing. Third thing, hold industry accountable. Set the bar high. Some people are going to make it, some aren't. And NASA should prune that CLIPS cohort, early and often, and use scheduled on-ramps to bring new people in. We just need to see that happening. And then fourth is accept risk. And I think Elon Musk sets a great example for the industry when he talks about risk in space launch and what might go wrong. It works because he's sincere, okay? And so we in the business know that not all flights end well, and so we just need to keep moving forward. And with that, I want to just close. The moon is chock full of resources. My fellows on the panel know this way better than I do, and they're better prepared to talk about the details. What we need is an extensive lunar resource prospecting program and designed to characterize the availability of each resource in different locations on the moon, not just at the poles and not just at the Apollo landing sites. And CLIPS, I think, is a really great mechanism to go do that. So thank you.
All right, great. We got about 45 minutes left for questions. Before we dive into those, I just wanted to thank Rob for bringing up CLIPS and NASA's current role. There was a workshop held in July back in Columbia, Maryland, called the Lunar ISRU Workshop. It was co-hosted by NASA and the Lunar Planetary Institute. Out of that workshop, I think there were a number of conclusions, but getting ground truth at the lunar poles and characterizing the nature of the water ice deposits that are there was the top strong recommendation, along with the fact that propellant is probably the first economically viable resource to be developed on the moon. That's been communicated to the Space Council by Dr. Clive Neal, who gave a 5-minute presentation there. It was actually echoed back to us by Vice President Pence. And just earlier this week, or early last week, the Office of Science and Technology Policy out of the White House published a 3- or 4-page document of the R&D policy priorities for the United States. Space was one of those. The very first highest priority for space research identified by the White House was lunar resources. So I think we're being heard. I think we're gaining momentum. I would echo Rob's concern that we got to make sure that NASA's listening and obeying the direction that's coming down from above. But with that, we'll open it up for questions, and I think, Mark, you came down first.
Yeah, I have a question for Chris Lewicki. If you had a great deal of political power in the United States and could change the laws, what would you do so that would be possible for what you sort of failed to do?
He's trying to find his voice.
I don't know the answer to that question.
You said there was no financial mechanism for.
Yeah.
Yeah.
Well, I guess it's more of a rephrasing it, knowing what I know today, how would I approach it differently? I don't think timing was an issue that is knowable.
Well, look, if you could create something like the stock market or
Yeah.
venture capital, what would you create?
Oh, I see what you're saying. Would you create a system? I think a system that allows, I guess, more capital to be available on a longer time frame. Like from an investment standpoint, whether it's the established models or even an angel investment, the timeline, unfortunately, is single-digit years.
Yeah. So how do you set up a mechanism for doing that?
I'm working at a blockchain company now. I think that is, there are a lot of solutions to problems as not yet unknown, or as not yet known in that area, and much like the beginning of the internet. Some of the things that look like crazy ideas today might be mainstay in 15 years. Some of the things that people are going to say are going to change the world are not going to. But what's interesting there is the way that it allows you to connect more disparate things in a more understandable way, in a more traceable way. So that you could, for example, create a financially invested shared community around a shared project which isn't defined as a U.S. C corporation. That also is a particular type of business engineering and tax engineering that companies in the U.S. today are operating within, that has worked very well for the problems it was designed to solve. But I think there's something different, and I don't have the answer today. But I think it's that type of thing, though, that it's not just the engineering, it's just not the science, not the policy, it's the financial engineering needs to move forward. And when I have the answer, I will be pitching it.
Okay.
So at the Space Resources Roundtable, it's an annual event that occurred at Colorado School of Mines, we had a pitch by a guy from Stanford, Bruce K. I don't know if you guys know him. Yeah. But he's been thinking about the idea of a space commodities futures market as one of the financial engineering solutions that could help raise capital and with a very long time horizon. So there's ideas out there. I don't know which one's going to work.
Yeah, I want to jump in there on that and echo that. We work with Bruce, and one of the things that Bruce talks about is that you don't even have to be able to access the material immediately. But let's just say, for example, we found a 100-meter across nickel iron meteorite chunk laying on the lunar surface. You could actually do a metals futures market based on that. And Bruce Cahan has laid the groundwork for that. And this summer, we had a group, it was called the Frontier Development Lab. It was sponsored by NASA Ames, Luxembourg, Intel, Google, NVIDIA, so Silicon Valley heavyweights in there. And we did an exercise to help raise the confidence level of these resources by going through existing data sets that are already out there, applying machine learning and artificial intelligence algorithms to tease out different resources. And we actually had a really good fundamental success in that this summer, and we're going to reiterate that with Bruce, but there's going to be a confidence level. And like right now, let's say we kind of know that there's metals on the surface, but the confidence level of where they're at is only like 0.4. What we did this summer is we think we kind of raised it to 0.5, but they only had 6 weeks to work. We have the data sets. We went through 35 terabytes of data. If we could get the confidence level to say 0.8, not even 100%, it allows Bruce to start the speculative end of the metals futures market, and that is something Wall Street understands. It's something that comes straight out of Stanford economics. Bruce is a professor at Stanford. So that is at least one thing that we're actually pretty close on.
Al?
Oh, yeah. I was wondering, what are the non-government end user customers for these systems? What I mean by end users, the communication satellite business is very, very strong because it has millions and millions of people who want to use their service. They don't want to buy it to sell it to somebody else. They want to use it. Okay? So is there a similar market driver for the systems that you're talking about? Now, obviously, one is government. Government wants to send stuff to Mars and send stuff to the moon, and you can sell them, propellant and stuff like that, possibly, if things work out. But are there any non-government, and that's not a huge market. I mean, it's not decent, it's decent, but it's not anything like communication satellites. Is there an end-user market that can drive all this? It can bring money from outside of the space world into the space world?
Okay, so I've kept a list of how do you make money in space for the last 20 years. And when I was at NASA, I got to know most of the companies that were working in space resources, and I got to a pretty good feel for all the business models. And there's like 47 things on the list. And some of them are crazy, like nursing homes on the moon because low gravity is good. If you fall down, you don't break your hip, But people insisted I add it to the list. But I got frustrated because it's hard to find small business models that make sense where you can make a profit in 7 or 8 years so your investors get an exit. It's really hard. I mean, isn't it, Chris? In your experience, is it hard to find these?
I don't think it's been demonstrated yet.
Yeah.
Where the customers are back on Earth.
So I got frustrated and I wrote a paper on how it's so cheap that the government should just do it as a government project. And then I thought this will be the beginning of a 10-year effort to convince the government. And I got an email within 3 days from the White House. Tom Khalil read my paper and said, "Oh, we love it. We want to do it." And then we spent a year and a half, but he said the bad news is we still can't convince Congress. So we have to find the coalition of the willing. So then we were pivoting again back towards the philanthropy, and and we spent a year and a half trying to find the coalition of the willing, and we never did. So it is a tough problem. And I think we're going to have to, I think it's going to take a lot of smart people to find solutions in the short term. George is working on his idea, rocket propellant. He's in a position to know. He was chief scientist at one of the largest rocket companies in the world, and he believes he's got a business model. And that serves the end user because you're putting communication satellites in space that serve customers. So you're providing value to customers on the Earth by mining water on the moon. Tourism, I used to poo-poo that, but I don't think we should. The lunar surface tourism may be big within a few decades, could be, possibly. I think that government's going to play a large role. I think that geopolitical pressures and military is going to play a large role, trying to get there first so that we can influence global policy. And I think the like Open Lunar Foundation and other philanthropic things are going to play it, like Jeff Bezos as a
as a visionary effort just because he wants to do it. I think that's going to play a large role. So I don't think there's a single simple answer, but I feel pretty confident in the weight of all these contributions that we're going to find our way over the next few decades. I'm sorry that's not a simple answer, but that's the one I've come to.
I've got two things that I'm thinking about that are kind of in that territory. Experiences in the category of tourism, I think, is the incremental one that's out there. There have only ever been 11 people at once in space. That's the top of the high water mark. But it's not unreasonable to expect that in 5-10 years' time, the access to space, the different commercial options that we have for getting there, the ability to repeat technology of years past much cheaper, and deploy it for entertainment experience, maybe even for industrial benefit, as side businesses, is things that there are probably many business models that close on dozens of customers for starting to do that. And I think that's something to get excited about. I think that a lot of the future space innovations will come from the caretakers of the Future Space Hotel, who on their off time have the world's best research environment for technology development as they're cleaning someone's quarters. And writing papers about the way that things behave in zero G. The other thing, bringing it back to space resources, is George mentioned in the introductory comment about how, in many ways, resources allow you to bring the cost down of things. The inverse of that statement is it allows you to scale things. And ultimately, I think our current approach to everything that we do in space is not scalable unless you start bringing external resources in. So whatever model that we have where we need to do something more than just a couple of times, or we need to do it for more than 11 people in space, that is the model that I think that grows, that gets fed by resources, by technology, by repeat customer, by competition, all those things. So it's in between the human experience of tourism and everything that comes off of that, and then all the side streams that are enabled by just more frequent activity.
And I'm going to add there is that we're not casting the net wide enough. Give you an example. There's a French company that, and I forget their name right now, they're the world leader in providing sapphire substrates. It's reasonably inexpensive right now. But the one of the resources that we have on the moon that nobody talks about is the vacuum. Now, this guy right here talks about how we can screw up the vacuum, and he's convinced me in some of his work. But the materials processing industry that is dependent on vacuum today is a $400 billion a year industry. And each and every time, if you go through the papers in materials science and materials processing, they say, there's ultra high vacuum is great, but it's very difficult and very expensive. And you read that on a multiplicity of different materials processing regimes. And so if you take that and if you look at what they're doing in the materials they're using, the atomic structure, the molecular structures, the vast majority of those materials exist on the moon. And so I've started taking a little different tact on it. And what we have been talking about for 30 years is the front end. It's, let's get there. How do we mine? How do we do this? But if you take a look at what industries that are out there, I talked to a guy in the steel industry from Australia, and I said, if you had this, this, and this, and he was going, oh my God, that would be so valuable. Or I go to O'Neill Steel in Birmingham, Alabama, or I go to Koch Industries. They're a $110 billion a year company, and $30 billion of that's material science. So we need to go out and cast our net wider to bring in a wider group of people and say, look, if you had this resource out there, what could you do with it? And every time I have had that discussion, it's been very positive. And so that's the direction I'm going.
I want to add one more thought. I was talking short term, it's challenging to find the commercially viable, smaller scaled business models. But long term, it's no brainer that space industry is going to provide huge values back to the consumers here on the earth. When you have a full or nearly fully closed supply chain in space, mining and manufacturing, then space beam solar power will be by far the cheapest form of energy that is available. I see John Mankins back there. I know John is looking at ways to launch it, economically profitable ways to launch it into space, but I know John's also mentioned that as mining and manufacturing in space becomes available, then you can start to make it there in space. And I'm convinced that once you can produce energy in space and move that entire sector of the economy off the planet, including all the mining and manufacturing that supports that sector, you know, making the steel for the oil rigs, making the mining trucks that mine the ore to make the steel, you know, the whole sector of the economy that supports energy. By the end of the century, that could be 4 times more industry than there is in the entirety of all industry on the earth today, because if you look at the way energy projections are toward the end of the century. So we could be talking about moving the equivalent of 4 times all of today's industry off the planet just by doing energy beaming from space. And so the value to humans on Earth, opportunity cost recovery for the use of the land that you're not covering with solar cells, the impact, the environmental impact that industry, the energy industry, won't have to pay because it's off the Earth, lowering the cost of energy. So there's huge economic value to consumers here on the Earth in the long run.
Thank you.
Mm-hmm.
Yeah, I had a question. To raise capital to exploit space resources, particularly physical resources, you have to properly define and ultimately protect property rights. So I'm wondering, how is that going to work moving forward? Because it seems to me that that's really a Gordian knot that needs to be addressed.
I'll start, I guess. It's a conversation which has picked up in this decade, and the U.S. took the first step in 2015 of the Commercial Launch Competitive Act and having 4 pages that discuss at least U.S. company ownership or U.S. person ownership of space resources. So the U.S., by taking that position, allowed a conversation and an interpretation of the 60-era treaties that was one that they were willing to back. Europe has followed suit, led by Luxembourg in doing that, and now it's seen as reasonable policy that you do something like that. Although it is super nascent in that it doesn't establish who owns any particular thing or what you have to do to own it. It just leaves those wonderful terms of art about obtaining things. One of the things I learned...
Possession, 90% of the law? I mean, can one robot or one person claim a whole celestial body, or you have a perimeter that you've defined?
It's somewhat irrelevant. And this is where the way that at least Congress defined it is if you're in a position to exploit that resource, your ability to do so legally won't be questioned. So that was helpful for them to say that out loud. What doesn't exist is if I spent 20 years and $20 billion investing in getting there to be in that position, how do I know that my position will be protected in year 19 before I'm there? Maybe when I've done 15 years of exploration and development and sorties and all those type of things. And that's a part of what I'm talking about that's absent in the space environment. It may not need to exist, but at least a mining company knows that at the end of the day, they've got title to the resource on the property that they're working with, and if it's a complete failure, they can sell that to someone else. So that doesn't exist in space yet. And here again, I think we have to get past 16th, 17th, 18th, 19th century ideas of ownership and territory and develop a 21st century mindset of, well, what does that look like? We haven't solved it for intellectual property yet. So, solving it for a resource in space is a similar challenge. But I think it's an issue that needs to be addressed because it provides certainty for not only people who are taking the risk, but people who are adjacent to that activity.
So there's been an international effort led by, out of the Netherlands, called the Hague Group. It's been sponsored by Leiden University over there, that has created a 19-point framework for the governance of space resource activities, which is fairly rational. I mean, it's trying to balance not squashing a nascent industry by over-regulating too soon, and trying to answer some of the concerns that the international community had when the United States did what it did in 2015. And they established things like an international body that would grant access rights, they call them. It's not ownership, but you can access a certain place, and establishes certain, sort of non-interference regimes where, as long as you're not interfering with what I'm doing over here, you can go over here and do what you want to do. Those sorts of things. I mean, I think it's a long way to go before something like that becomes recognized or signed as a treaty. And until then, it's a little bit like the Wild West. If you're an American company, you can go and establish yourself somewhere like at one of the poles of the moon and extract the water. You can own the water. You don't own the land you're sitting on, but you can own the water. And that's, I think, good enough for the short term. Rand?
Yeah, he stole my question, but let me expand on it a little bit. If we could own the land, would that help?
It just becomes more familiar to how people make investments and take risks, and create legal and financial instruments related to that dynamic.
Okay, because I could give a speech on this because it's in my current wheelhouse, but because we are working some issues on that, trying to do some multilateral agreements to interpret it. I'm not sure we need to come up with new ways. So much of doing this is figuring out how we can do the old ways in the solar system. Can we extend English common law, make the solar system safe for English common law? And that's kind of the project that I'm working right now.
Well, I want to jump in here on something as well. I've done some comparative analysis on this, and in a way, and I used to have this discussion with John when we're talking Mankins when we're talking space solar power. I always argued with trying to design a space solar power system to deliver power at 3 cents a kilowatt hour. There's a lot of places in the world that was just happy at $25, $50 a kilowatt hour, which makes solar power satellites a lot better. When you talk about space resources, it's not that clear cut on the Earth either. Rio Tinto was building a $7 billion copper mine in South America. And every few months, the government would say, well, you need to build a power plant over here for our people. And I say, well, okay. Well, you need to build this village. You need to do this. You need to, oh, by the way, China's just come in and outbid you for something that you've already paid for, so we're going to give it to them. So it's political risk in mining on the Earth is a huge factor. And one of the things, and I've had this discussion with John Chapman, who's a big Canadian mining guy, at some point, the political risk of mining on the Earth, and Rio Tinto and Anglo American or Barrick Gold, they'll spend $3 billion, $5 billion, $7 billion to develop a property and then lose it.
Yeah, happened to Barrick Gold in Tanzania.
Exactly. So I don't want us to go down this, oh my God, we have to reach this wonderful, purist kind of position here in these things. As long as we can make the overall risk equation, and that equation has several different dimensions and several different variables, if we can bring that risk equation lower for extraterrestrial mining and resource acquisition to an equivalent project, say Rio Tinto in Chile or Rio Tinto on the moon, and make that equation balance better for the moon, we're going to win.
Sticking to property rights for a second, I think everyone here should actually applaud Chris for all the work he did to get that agreement done in 2015, because it was an incredible amount of progress. So
I wouldn't advise meeting with that many senators and congressmen.
The other thing is and I'm from Canada, I'm going to speak on the economics panel, but when you look at history and you look at the precedents of how things were structured in them, and we have much more of a mining industry than the US does, you know, how you determine claims and everything like that, it's a crucial issue that I don't think is at least bit resolved as far as extraterrestrial resources are concerned. But it was determined by the miners themselves. So I think until there's more activity, nobody really wants the Hague telling potential miners what to do.
Well, that's the big underlying part of the challenge is there is a desire for there to be a place to go for a body or a power structure to decree. And that's easy when you're operating within the territorial boundaries of the country. That's all set out pretty well. And it's even set out pretty well in colonial times because you would just have a fight about it and settle it. And we don't really want to repeat those years either. But here again, you know, the mechanism of having an international body that says yea verily or no verily, there comes to bring all sorts of political elements in it, some of which are productive, many of which are not. So a lot of it, I think, like you just mentioned, with you know, industry collaborations and industry practices. For people to agree, as we've got an international multilateral agreement on the space station, that, well, if it's in the Japanese module, we'll do it the Japanese way. If it's in the Russian module, we'll do it the Russian way. I think we can, for the people who are doing the activity, negotiate to make sure that everyone's got enough elbow room when things are going on, with probably a prevailing prioritization of the common good while we're all doing that. And that again, is a new model of governance, which we get better and better at every decade with occasional setbacks.
Well, but even under the existing regime, with just the Outer Space Treaty and the 2015, you know, CLSA, a private company entity in the United States is still subject to oversight by the U.S. government. The Outer Space Treaty says that, you know, the U.S. government is, you know, required to approve and in fact control the activities of private persons in space. And so regardless...
They're not controlled, they're just liable for it.
Yeah. I think the word control is actually...
Which implies some control.
Supervise. Supervise. So, you know, you know, if you're a launch company, you get supervised by the, you know, the launch licensing process out of the FAA. You know, the Space Policy Directive number 2 designated the Commerce Department as the agency that would supervise all other activities beyond launch and reentry. And right now, there's a directorate being stood up. They don't have rules yet. They don't have funding yet. Congress hasn't decided to fund them. But no matter what, if you're a space mining company, you're going to have some level of government supervision. That's
better for it to be in the Commerce Department than in the Department of State.
I totally agree.
One of the things most people don't realize about ISS is that the Kibo module is Japanese sovereign territory. Same thing with the Russian module.
Yep.
Just a little note on the ISS. When the ISS was put up, all the countries involved in it were party to creating an ISS legal agreement for how it was operated, including Canada, because we were a participant in it as well. And Jeff Manber at NanoRacks at one point in time was saying to me how he thought it was the best legal agreement that he has ever been involved in. And because it meant in so many different areas and with different countries involved in different components, it all worked. And a friend of mine was one of the lawyers who drafted it for Canada, and it sure made his day when I passed that on. So it's interesting to say, well, there is this legal agreement for outer space, and it's working quite well. So what else can we do along those lines?
Well, I would like to say that I don't know if anybody else shares this fear, but I don't think the Outer Space Treaty is going to survive till the end of the century, because it has a clause that says any country can get out of it with just 1 year notice. They have to just send letters to the through the depository nations to say we're out. And then 1 year after the date of that letter, they're no longer bound by it. They could claim the moon if they wanted to. And as technology goes the direction it's going to be increasingly easy to do things on the moon. And I think there comes a point where countries aren't going to want to be in that treaty anymore.
Is that good or bad, Phil?
Yeah. Well,
I don't know about good or bad. I think we just need to be making decisions along the way to get the outcome we think the world needs for it to be a good world at the end of that.
And maybe just to your point, Phil, there's another pressure, maybe the principle of non-interference perimeters. That might come before that pressure of secession breaks.
Yeah. Well, so for example, when you land on the moon, you spray lunar soil at 2 to 3 kilometers per second, comparable to the velocity of your rocket exhaust. And a vehicle the size of the lunar module sent ejecta globally around the moon, although it's very small flux at a distance, right? But it is globally, including some ejecta goes completely off the moon, and you can sandblast orbiting vehicles by landing on the moon. You could destroy a spacecraft that's in orbit if you land at the wrong time. So at some point, countries are going to say, well, I have a really expensive telescope. I just put it in the middle of Shackleton Crater, and we need a 10-kilometer blast radius around it so nobody can land within 10 kilometers. You've just claimed Shackleton Crater because nobody can get into Shackleton Crater now. So we have to figure that out. We have to figure out how to play well with other countries on the moon.
A lot of this, reflecting on it, I think is just a symptom of a bigger problem. We spent a lot of time discussing the whys and wherefores of the legal challenges and the legal certainties, because there has not yet been so compelling of a reason just to go out and do it and overcome all those challenges anyway. So it's a fun thing to talk about, but ultimately it doesn't matter. We will solve the legal problems when there is a clear need to. And I'm confident that it's a solvable problem. But it seems to be a fun thing to talk about. So
yeah, and I'm actually optimistic because I think these problems are going to drive us to get to the moon faster, because everybody's going to worry that somebody else is going to set the policy, and we want to be involved in setting the policy. In order to do that, we've got to be there.
Well, the precedent, which is one of the most important legal concepts in the world, really. So,
Yeah,
well, in
so
common
we're
law,
going
it
to
is.
figure it out.
precedent is 9/10 of the law.
All right, let's go over here.
Yeah. Kind of building on that, one of the things that's really striking about the work from the 1970s is you can kind of track this utopian thread that gets endlessly deferred throughout and into the 80s. The project started out supported by Stuart Brand and aspects of the counterculture. And I want to maybe connect a couple of things that people set up here and ask about, other political and even economic models. George, I was really glad you brought up the end of scarcity in your introduction as a potential, side effect, or is that a primary goal? And then Chris, you were talking about the design of financial instruments, as something that we should remember is still possible, right? Is there another way to think about that, think about both of those things together so that the high frontier redux doesn't sort of break down into trickle-down redux as we depend on economic prosperity to generate something like the end of scarcity?
There's a thing that I reflect on with an objection that often comes up in a room this size, where someone will say, well, not everyone's going to want to do that. And I said, well, I hope not. Not everyone from Europe wanted to go west. Imagine if they all did. With 7 billion people on the planet, it doesn't take too many for there to be an imperative of people creating opportunities and innovating and doing things they want to do that don't necessarily involve continuing doing them the way that we do in the service of the Earth. Large fraction of those 7 billion people are going to still be here, hopefully, happily so. So I guess it's, for me, we don't have to choose between this or that. We can do both of them. For me, that's what the utopia boils down to, is, this too is possible and worth doing. not because I have to justify it to someone else. I only have to justify it to myself and everyone who I'm asking to do it with me. So, at least in my viewpoint, and I probably share this with many people in the room, I think the world would be much more interesting if we could get off the world. So I spend a lot of time working on that. And I don't need to necessarily impose it on anyone else that, this is the way that the world needs to be. I go create it for myself. So it's a little bit made a response to your question, but that's my take.
Yeah, I'm not sure I completely understood your question, but I get nervous when people talk about, utopias in the sense that they would be imposed utopias by, central planning organizations that understand what utopia means. I think utopia is best achieved by, an abundance of resources, that are available cheaply and individual decisions, making, choices to transact with each other or not, and the freedom, like Chris was saying, if you want to go off planet, you go off planet. If you don't, you don't. And that organically in a self-organizing system is a better way to get to utopia in a world with abundant resources.
I guess I'm asking in that case, how does scarcity end? Or does scarcity just end for people who choose to participate in this economic and resource exploitation system?
Scarcity ends because resources become really cheap. Imagine if, in a world with, gigawatt solar power stations orbiting, in geosync, that everybody has access around the world to energy of, that's pennies per kilowatt or lower. That's how scarcity ends.
In some way, scarcity has already ended. There's over 2 billion of these out there right now. 2 billion out of 7 billion people.
Okay, we've got time for 2 more questions, and then let's wrap things up.
Aha, I'm back.
Back.
So going from the large scale down to the small scale, and I had to write this down because the regulatory stuff was actually really interesting. But a little more practically, what mechanisms or machines will we need for these mining operations, if you will? And how will this, being in space, 0G, or in a vacuum, impact how we currently have our mining operations set up, if you will? And this is more for the short term, because as you were mentioning, the long term, it's always obvious.
Power starts it out. We're already talking, did a paper in 2015 on site selection, 100 kilowatt power towers. You need, NASA always way under budgets power, but we posited somewhere between 700 kilowatts to a megawatt of, call it nameplate power, which ends up to be about 700 kilowatts of real power, with buying 10 of the landers from Blue to put it on the surface. There's been discussions with the government to actually have the federal government buy 10 of those and put them on the lunar surface. So you start with that, and then you go to Phil.
Okay, so for mining robots, Jim Caravala is working on mining robots. He's got his preferred method. We have a robotic mining competition at NASA that we've been doing for a decade now. That encourages a strip mining approach, excavating regolith. Then you've got George, who's working on thermal extraction methods. So there's a huge variety of concepts for how to do the mining. The one thing we don't have really is ground truth on the data, on the resource. And we don't have any tests in situ of how to extract. So I think we've really got to get some missions on the surface trying it, and then the trade space will start to narrow down. Until then, we're all just taking our best guesses and trying to be first in by developing what we think is going to be best.
It's one of the biggest challenges, I think, in the in-space environment is access to a relevant test environment. In Mojave, you can roll up the door and push your experiment out and create some results that you know should be translatable to your work down the road. I guess things that I would add on, Dennis mentioned about being able to map with greater certainty exactly where certain things are there, how much is there, how much you can plan on, because the process that you would plan on implementing is going to depend enough on those details that you'll need to tailor it for that, at least to do it efficiently and scale it. In most of these processes, you have to, since we're talking about human-robotic partnerships, but leveraging as much of the robots as we can, which means lots of autonomy, but a lot of these things aren't necessarily perpetually autonomous. You're going to have inefficiencies, you're going to have contaminants and things that you'll need to deal with that the only way to know those things is to figure out what breaks over time and address those issues. And I think the way that we transport things around also is it's even harder than we thought it was when we're looking at planetary resources. You know, if you get locked hydrogen or you get water ice and ship it in cube form to the Earth-Moon system, sure, you can give up half of it in terms of getting from point A to point B, but the trades of actually doing that also end up with you know, are you going to make a kiloton, a megaton, or a gigaton? Because the way that you would approach those problems are also very different. So it mostly depends on, you know, which one do you have to address, and then you can trust in the engineers and scientists to
Well, for small scale, to start off, if you will, when you start getting into the higher orders of magnitude, then I can presume that we're
I think one of the first uses of space resources will be construction with regolith to build landing pads to address this problem of landing on the moon without spraying everybody. And so
containment berms.
Berms, but also sintering the soil to make competent pads you can land on, or spraying polymer, or there's like a dozen different technologies for making a competent surface. And so I think one of the early applications of space resources will be construction with raw regolith. Another early thing will be extracting metal from regolith. You can either beneficiate the soil to pull out the free metal grains that are already there, because the moon has been collecting metal for billions of years. It's about a percent of the soil is free metal on the moon. And you can beneficiate that.
Yeah.
And then, so beneficiating metal and making things out of metal. Somebody asked about what's the first part that'll be made. Jim Logan asked that. You could pretty easily today get metal out of the lunar soil, and then like Chris.
Laser blade.
Like Chris did, you could make parts out of that.
Yeah, when we did the direct laser melt of a Campo de Cielo meteorite, about 40 kilos of it, to create the powder bed for that, one of the things that I insisted was that they don't purify it. Leave all the crap in, so that, you know, see how well the system does with an imperfect material going into it, because you're probably not going to have the luxury to do that early on.
And there are a lot of studies going on. ULA has sponsored a study. JPL just completed a study designing a lunar mining outpost, including all the water purification, and we did basic point designs on a lot of the equipment. So there's a lot of studies going on.
Yeah, let's wrap it up and get one more question in.
I'll do the quick one again then, because I had a couple. The Chandrayaan suite of instruments that's orbiting the moon right now, do those instruments allow increased confidence that would push that paradigm for investors enough to consider investment?
Chandrayaan has some great instruments, and I think it will help. I think we, right now, based on what we did this summer, I think we're almost at the threshold, but Chandrayaan will absolutely help. I just wish that the lander had been successful. It would have been amazingly helpful for George and the water experiments.
Yeah, I think the consensus of the community through a couple of workshops and a few league meetings, lunar exploration analysis group meetings, you know, we've got what we need for the short term from remote sensing. What we need is ground truth. We need to go into one of these permanently shadowed regions near the poles and see what's really there and what the characteristics of the material really is. And then we can really design a mining approach. Right now, we're kind of speculating as to what's there.
And there's part of that, too, that it's not just confirming that remote sensing works. That's something that, you know, Well, it's not even that. It's the psychological effect of saying, yes, we understand this, we've been there, and we can produce this result physically. You know, it's the difference of demonstrating that the equation works versus building a machine that demonstrates the equation works. So the psychological effect of actually doing something and getting ground truth is very important.
Yeah, the one addition I'd make is a high-power radar, and I can tell you this, it's not public information yet, but we had one of these small satellite radar companies was actually able to detect a meteorite, a metal meteorite sitting on the surface of the Earth. So we know where it's at. It's Hoba. It's the Hoba meteorite in Groenfontein, South Africa, and we were able to detect that from space. So we know we can detect it.
It's a very big meteorite.
Well, it's it's not that big. It's 4 meters by 4 meters, so it's not that big. It's only 80 tons.
Yeah.
But there's going to be a lot of those on the moon, and so we have detected that. So a high-power radar in lunar orbit is going to find the metal, and it's going to find a lot of it based on the work that we did this summer. So our confidence level is increasing daily right now.
All right, so with that, we're out of time, and let's have a round of applause for the panel.
Okay, thank you very much to all our panelists, and thank you to the audience as well, and we'll see you back here tomorrow morning at 9 a.m.